Hello everyone and welcome to the first episode of Let's Upsolve. I just finished upsolving Codeforces Educational Round 125, problems A through D, and I'm going to be explaining my solutions. I urge all of you to try solving the problems on your own at first. Then if you get stuck or just want to see the way I solved it, you can watch the rest of the video. Alright, let's get into problem A. In problem A, we had to move a chip from the point 0, 0 to the point x, y in a coordinate plane. To move the chip, we were given an operation. We can move the chip from point x1, y1 to x2, y2 if the Euclidean distance between these 2 points is an integer. Now, the first thing that you need to notice is that this is always possible in at most 2 moves. So let's say we have 0, 0 and we want to move it here to x, y. What we can always do is first move it to x, 0, then move it to x, y. So the Euclidean distance of this is obviously an integer and the Euclidean distance of this is also an integer. After this, we needed to find 2 more sort of edge cases. But we were given both of those edge cases in the example input, so it wasn't very hard to find. There's a case when x, y equals 0, 0. In that case, of course, we don't need to make any moves because it's already in the desired location. The other case is if the Euclidean distance from 0, 0 to x, y is an integer. And in that case, we just had to check if x squared plus y squared is a complete square, or if the square root of this number is an integer. The way I did this is I read in x, y, I got this sum, which is the square sum of x and y. And then I split it up into the cases that we just found. So if the sum is 0, it means that it's already in the desired location. In the other case, I'm going to find the square root of sum. If the square root of sum is an integer, or if I find the square root of sum, then I'm going to print 1. In the other case, I'll just print 2 because we know that we can always solve it in 2 with the construction showed here. In problem B, we were given 4 integers n, b, x, and y, and we had to build a sequence of length n, well actually of length n plus 1, because it's from 0 to n, where a0 or a null is equal to 0, and for each I bigger than or equal to 1, we can either increase it by x, or so the next element will be the last element plus x, or decrease by y, so the next element will be the last element minus y. And our goal is to build a sequence such that all ai are smaller than or equal to b, which we are given in the input, and the sum of the sequence that we built is maximum possible. Now in this problem, I thought about it for a bit, and there seems to be an obvious greedy solution. What we basically do is, if we can, so if ai minus 1 plus x is smaller than or equal to b, then we increase it by b. Otherwise, if we can't increase it, then we'll decrease it by y. What I did is coded this solution and sort of did like proof by submission. So I submitted and it got accepted. Here's the code for it. So I don't even store the whole array, I just store the current element. If I can increase it by x, then I'll add x. I'll increase the sum over the sum of the whole array by this current number. Otherwise, I'll decrease it by y. we're going to be proving the correctness of this greedy strategy with proof by contradiction. So first of all, let's assume that we have some array AI, AI plus 1, which is optimal and it doesn't follow the greedy strategy. So at some point, if it doesn't follow our greedy strategy, then at some point in the array, there's going to be an AI plus 1, which equals AI minus y. And we also know that AI plus x is smaller than or equal to b. If there are no positions like this, then our greedy strategy was followed. So in this array, there must be some position where this holds true. Well, I'm going to be proving that in this case, I can always construct a bigger sum, an array that has a bigger sum. First of all, let's find an integer j, which is bigger than I, where aj equals aj minus 1 plus x. If this j doesn't exist, well, then what we can do is just change ai plus 1 into ai plus x, and the total sum for this array has been increased by x plus y. Because after this point, if this aj doesn't exist, we know that for all subsequent i's, all we do is decrease it by y, so this won't cause a problem further on in the array. It won't go over b. In the case that a j does exist, so there is a j where we increase the array, let's see what happens if we swap these two operations. So what we do is, after ai, we have ai plus x, and then dot dot dot, and then aj minus 1 minus y. This is I plus 1 dot 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 j. Let's see what happened. Before this, the array from I to j looked something like this. It looked like ai, then ai minus y, then ai minus 2y, then ai minus 3y, etc. up until j, where we had aj minus 1 and then aj minus 1 plus x. In the new version of the array, we can see that all of the elements are increased by x plus y. So now ai plus 1 becomes ai plus x, and then ai plus 2 becomes ai plus x minus y, and aj will not have changed, so it will remain the same as it did here, because aj will equal ai minus j minus I times y plus x. The only difference is that previously we added the x last, and now we're adding the x here in the beginning. So what we proved is that by swapping the operation at ai and aj, we get an array for which the conditions still hold. So for all elements, ai is smaller than or equal to b. and the sum of this array, will be strictly larger than the sum of the previous array. So we arrived to a contradiction because we supposed that the array AI is optimal, but clearly it isn't, because if we swap the elements at AI and AJ, we're gonna be left with a larger array. In problem C, we were given a bracket sequence of n characters, and we were given a sort of operation that we had to perform with it. This operation is, we have to choose the shortest good prefix, and a prefix is good if it's a regular bracket sequence, or if it's a palindrome of length at least 2. So here are the examples. A regular bracket sequence is a bracket sequence that we can insert pluses and ones into. There's a method for finding regular bracket sequences, which is pretty easy, but it turns out we don't need that at all for this problem. Because after playing around with it for a little while, I made some pretty cool observations. So I'll jump right into it. Let's say that the first bracket that we encounter is an opening bracket. What can be the next bracket? Well, it can be an opening, then a closing bracket, or an opening, then another opening bracket. Well, an opening and a closing bracket is a regular bracket sequence, so then that's going to be the shortest prefix, and we're going to delete that. And two opening brackets next to each other is going to be a palindrome, because it's like this, AA. It's the same backwards and forwards. So if the first letter of the current segment that we're looking at is an opening bracket, then we just delete the next two elements, of course check if there are two elements, and move on. The second case is if the first element is a closing bracket. Well, if there's another closing bracket following it, then it's a palindrome and we just delete it. For the same reason, it's the same forwards and backwards. And the other possibility is if after a closing bracket we have an opening bracket. This is like the trickiest case of the problem, but even this is handled pretty simply. If we have a closing bracket somewhere, then that's gonna close this palindrome. So what we can essentially have is a closing bracket, some number of opening brackets, which is 0 or more, and then we also have this case included in this case, because this case is basically just this with 0 opening brackets between the two closing brackets. And then, so we have 0 or more opening brackets and the closing bracket to close it off. And this is going to be a palindrome because it's the same forwards and backwards. We know that the string will either end at some point, like it will end here, and then we cannot really do anything about this case, or we will run into a closing bracket and then we'll delete this as the shortest prefix that is good. Implementation was also pretty simple, but we did need to watch out for a few edge cases. So what I do is I go with, I have the current position stored in pos, and while this is smaller than n minus 2, if we see an opening bracket, then we just increase position by 2, and the count of the number of segments is also increased. If it's a closing bracket, then I'll check if the number after it is, or the letter after it is also a closing bracket. It seems I, for some reason, didn't merge these two cases into one. And the second thing I do is I do the other half of that case, so I see if there are any opening brackets between the two closing brackets, and then if we come to the end of the string without this palindrome being fully realized, then we'll break off the while loop and print out the number of segments that we deleted and the length of the remaining segment. In problem D, we were given some sort of strategy game where we had to defeat M monsters using as little money as possible. To defeat a monster, first we can build a squad, and we can build a squad for each fight. A squad contains some number of a type of unit. We have n types of units. Each unit has some cost, some damage, and some health. When a monster of health H and damage D fight a squad of strength K times D and health H, what happens, so in here our squad is made up of K units who all have D damage and H health. What happens is that over 1 second our squad deals K times D damage to the monster, and over that same time period the monster deals D damage to the health of all of the troops. This damage is not dealt once per second, but it's dealt gradually over 1 second. So in 0.5 seconds, we're gonna deal 0.5 times K times D damage. In A over B seconds, we're gonna deal A over B times K times D damage. That's really important. All of the units also have some cost, CI, and to build a squad of size K will cost CI times K money. And we had to defeat all of the bosses or all of the monsters using as little money as possible, but at most using capital C amount of money, and that's also going to be important in the solution. First of all, let's see how much money it costs for the ith unit to defeat the jth monster. Basically, what we do is we calculate how many of the ith unit we need to recruit to defeat the jth monster. Well, first of all, let's see how fast the jth monster will defeat the ith unit. Well, we know that the jth monster has damage dj, and it's gonna defeat our unit in x seconds. We know that dj times x is equal to hi, because it defeats so we need to multiply its damage by x seconds, and if it equals hi, then our unit is defeated. Let's move this around and we get the equation x equals hi over dj. This is the amount of time for the monster to defeat us. Now let's see how fast it takes for our squad to defeat the monster. Well, we're gonna have a damage of di times a, and a is gonna be the number of units that we recruit. Di times a times x is equal to hj. In this case, x, the amount of time for us to defeat the monster, is hj over di times a. Now if we want to defeat the monster with our unit, what we have to do is we have to make sure that this x is smaller than this x. So hj divided by di times a is smaller than hi over dj. Alright, let's move some things around, and we are left with h, say, then dj smaller than hi times dj times a. And so that's pretty neat. The next thing we can do is, from this we generalize the problem a bit. So let's call xi, or xi will be or xj will be the strength of the jth monster, which equals hj times dj. And let's call the strength of unit I, and this is this is di. Let's call the strength of unit I. I called it in my code for some reason. I called it vi, so I'll just stick with it. Vi equals hi times di. Of course, for us to defeat this monster, we're gonna need A times Ci coins, and we'd like to minimize that. The first thing I noticed is that it would be very helpful if we can build some array best I, where best I is the largest strength of a squad that we can build using I or less coins. Basically, this will be helpful because after this array is built, for all monsters, we just need to binary search the number xj in this array. If it's not in the array, then we cannot solve the problem. We cannot defeat the monster using less than C coins. And this is where C comes in handy, because the size of best is at most C, which is smaller than or equal to 10 to the 6th. And the hard part of the problem, I guess, is trying to construct this array best I. That's what I'm going to be explaining. The first thing that we can do is construct an array best I, where best I is equal to the largest strength that we can get if we use exactly I coins. Well, first of all, when we read in the inputs, we're gonna update best I. So when we read in Ci, Hi, Di, we're gonna update best of Ci with Hi times Di. Well, we're not gonna update it for certain. We're gonna update it if it's bigger than the current value in Ci. After this, the next thing that we need to do is try to iterate over all I from 1 to C, and try to find the best way to construct an army of cost exactly I. The way we can do this, for let's say that we're at some I and we want to construct the best army, let's say I is equal to 10. Well, the way we can construct an army of size 10, we can have a unit which costs 10 and have its power. We can have 2 units of cost 5. We can have, well, 10 was a pretty lazy example, but then we can have 10 units of cost 1. So what we realize, for a unit of cost I, we can get, for an army of cost I, we can achieve building this army by looking at all of I's divisors and building the army up from there. This way, what we can do is we go over all I, then for all I, we go over all of the divisors of I. That's gonna take square root c time, and we're gonna update best I with best I is gonna be updated by best, let's say j is a divisor of I, best j times I divided by j. It's as easy as that. Now, after we update these best values, we need to transform from best I being equal to the largest army that we can build with exactly I coins to the largest army that we can build with at most I coins. And we can do that with a simple for loop and taking prefix maximums over the array best. And with this, we're basically done with the problem. There's one problem left, and that's that this solution might be a little bit slow because it takes c times square root of c time. What I found is that actually, which can be pretty big, to like 10 to the 9th. What I found is that it actually passes. It passes much slower than the other solution that I'll also try to explain. But it passes. So in this code, we first read in all the numbers and apply the best values for for when we recruit only one unit. Then we go over all I that's smaller than or equal to c, and we go over all of its divisors and try to build an army of units of cost j, and we take I divided by j number of units that cost j and take the maximum value of these. After with this, we go over the prefix and take all prefix maximums, and then we just do a binary search or upper bound. That's because we need our army to be strictly stronger than the monster. And then we print out the solution. The other way that we can solve this problem is not to go over all of the divisors of all the numbers I, because then we're gonna go over numbers that actually don't divide I. So for example, in 20, we're gonna go over all numbers from 1 to the square root of 20. And of course, the square root of 20 is about, well, 20 is not a very good example. Let's say, alright, I don't know, 100. The square root of 100 is 10, so we'll go through all the numbers 1, 2, 3, 4, 5, 6, dot, dot, dot. And we can already see that, for example, 3, we're going to check if 3 is a divisor, but 3 isn't a divisor, and that's sort of like wasting time. So what if we could go through only the divisors of all numbers? And this is actually possible if we do something like this. So first we do for I equals 1 to c, and for j equals I, j is smaller than or equal to c, and we increase j by I. So we go over all of the multiples of all I from 1 to c. This way we can get all the multiples of 6, for example. So when we have I equal to 6, we're going to iterate over numbers 6, 12, 18, etc. And when we're at a certain multiple of 6, let's say 18, then we'll check if it's worth building the army of 3 units which each cost 6. So we're gonna check 3 times best 6. This way we're gonna go over all the multiples of all the numbers from 1 to c, and it's also gonna be much faster because we're only going over like actual multiples. It's gonna cost first we go 1 by 1, so that's gonna c over 1, then we go two numbers at a time, so that's gonna be c over 2, c over 3, c over c, and the sum of this is equal to grows as fast as logarithm c. So if we solve the problem in this way, we're gonna get a complexity of c log c. Let's go over the solution, and you can see that it's a bit faster. Well, it's I don't know, 4 times as fast or 5 times as fast, depending on which submission we look at. And I only change this line of the code, so I go over I, then I iterate over j, and then I take for each j I take the maximum of best I. So for example, if I equals 6, then I go over all the multiples of 6, and I take the maximum of I take the case where I build my army of units of cost 6, and I use j divided by I number of units of cost 6 to build the army of cost j, and I see which of these armies will be the best. One thing that I got sort of stuck on is the idea that when we were at I equals 2, best 6 was updated using an army of cost 2. So let's say that the best army of cost 6 is equal to the best hiring 3 of the best units that cost 2. And after we updated best 6 at I equals 6, when updating, for example, best 18, we're using this updated version of best 6. And this is sort of like a red flag when doing any kind of DP, because there's the possibility of counting things twice or doing things that are not actually possible. But in this case, it doesn't really matter, because if we have best 6 equal to 3 times the unit of cost 2, so best 2, well, we can just take 3 times best 2 times 3, so that's 9 times best 2 for best 18. And I realized this, but it doesn't actually matter, because when we were doing I equals 2, best 18 was already updated to this, so best 6 will never affect best 18 if best 6 is updated using best 2. So that's not gonna cause any problems. Thank you for watching this video. I hope it helped, and I'll see you guys again in the next video.